Welcome to this explainer. We're about to take an absolutely epic journey into the dark, mysterious heart of the Milky Way. We're going to travel 26,000 light-years away from our quiet little corner of the solar system, straight into a chaotic, bubbling environment that literally governs the physics of our entire galaxy.
For decades, scientists have been practically pulling their hair out trying to peer through these incredibly thick clouds of interstellar dust. They all wanted to answer one huge question. What exactly is lurking at the very center of our galaxy? What is this incredibly massive, invisible anchor holding the whole Milky Way together? Well, today, we are going to solve this cosmic detective story. We'll look at how astronomers actually found it, how they managed to take a picture of something completely invisible, which sounds impossible, I know, and what these newly discovered magnetic flares and galactic winds are teaching us about the universe. Section 1. Finding the Galactic Center. Let's dive right into this 50-year quest to locate and actually prove the existence of the supermassive black hole powering our galaxy. Okay, so let's rewind to 1974. Picture this, two young astronomers, Bruce Ballack and Robert Brown, are at the Green Bank Observatory in West Virginia. Now, they were actually just looking for star formation regions, but kind of just for the heck of it, they decided to point their antennas directly at the galactic center in the constellation Saggitarius, and suddenly, bam! They detected this unbelievably strong, concentrated radio signal. 8 years later, in 1982, Brown would actually give this compact radio source a name, Saggitarius A star, using the asterisk symbol from atomic physics to show just how highly excited and energetic it was. Fast forward to the 1990s, and scientists were mapping stars moving around this exact spot. And then finally, in 2022, we got the very first picture of it. But wait, let's jump back for a second to that initial discovery in '74, because the researchers actually hesitated to claim they'd found a black hole.
Why the hesitation? Well, the idea of supermassive black holes was just so radical at the time that the discoverers didn't want to risk their academic reputations. I mean, Bruce Ballack literally said he wanted to make sure he passed the laugh test. Even Albert Einstein, the guy whose math predicted black holes in the first place, had his doubts that they could actually exist in nature. So in their groundbreaking 6-page paper, Ballack and Brown never even used the term black hole. They just called it a physical structure that defines the galactic center. It would take decades of really painstaking observation to definitively prove what it was.
And what they eventually found was just mind-blowing. Astronomers mapped the orbits of stars, like one named S2, whipping around an invisible central point over nearly 3 decades. S2 moves on this highly elliptical orbit, accelerating to a staggering 7,000 kilometers per second when it gets close to Sagittarius A star. By calculating the gravitational pull you'd need to sling a whole star around at that speed, they proved that an object with the mass of 4 million of our suns was somehow squeezed into a space roughly the size of our solar system. Now, in physics, there is only one thing that can be that heavy and that small: a supermassive black hole.
Section 2. Photographing the invisible. Because, knowing it's there is one thing, but actually capturing an image of a completely invisible object, that's another beast entirely. To do it, scientists created the Event Horizon Telescope, or the EHT. Now, this wasn't just a single telescope you peek through. It was a massive global network of 8 linked radio observatories stretching everywhere from Antarctica to Spain to Chile. By syncing them perfectly using atomic clocks, they essentially turned the entire planet into a single Earth-sized virtual telescope. And trust me, they needed every single bit of that resolving power. Because Sagittarius A star is 27,000 light-years away. Looking for it in the night sky is literally like trying to take a crystal-clear photograph of a donut sitting on the surface of the moon.
The EHT had famously photographed a different black hole back in 2019, but our local black hole was a monumental challenge. Why? Because the glowing gas around Sagittarius A star moves at nearly the speed of light. It's completing orbits in mere minutes. EHT scientist Chi-Kwang Chan completely hit the nail on the head when he compared it to trying to take a clear picture of a puppy quickly chasing its tail. The target was constantly shifting, bubbling, and changing its pattern the whole time the telescopes were trying to capture it. It took over 300 researchers and 5 years of supercomputer processing to average out that blur and finally reveal the hidden structure.
When the final result dropped, it was spectacular. What you're looking at isn't the black hole itself, but its shadow. It's this stunning, glowing ring of orange plasma. And more recently, the EHT released a polarized light version of the image. The swirling lines you see? Those are the visible, highly organized magnetic fields spiraling right at the edge of the event horizon. By capturing polarized light, astronomers can actually map the magnetic forces that thread through the hot gas that the black hole is constantly feeding on. It's absolutely incredible.
Section 3. A Tale of Two Giants.
With our local black hole finally imaged, scientists had a second target to compare to their first famous discovery, M87 star. Comparing these two giants is a real game-changer for our understanding of the universe. When we look at M87 star, it is an absolute monster. We're talking over 1,000 times larger and 1,000 times more massive than Saggitarius A star. Its gas takes days or even weeks to orbit. Yet, despite these massive differences in scale and environment, right near the edge of the event horizon, they look amazingly identical. They both have that distinct ring of light and a dark shadow. This brilliantly proves that Einstein's general relativity governs these extreme environments universally. Gravity scales perfectly, whether the black hole is small or a giant.
Section 4. The bubbling accretion disk. Let's zoom in even closer now, onto the chaotic, dynamic environment right outside the point of no return. Because Sagittarius A star, it is definitely not just sitting there quietly.
Recent data from the James Webb Space Telescope reveals that SGR A star never rests. Over 48 hours of observation, astronomers realized it is constantly bubbling. They describe the accretion disk, which is that ring of gas falling into the hole, kind of like a river. Random, faint flickers are constantly happening, acting like small ripples on the water's surface. But then, completely unpredictably, there are these blinding, bright flares that act like massive tidal waves. And the material caught in these bursts, it's being whipped around the black hole at a staggering 30% the speed of light. So the really crucial point here is understanding what causes these massive tidal waves. Astronomers believe these blinding daily eruptions happen due to something called magnetic reconnection. Remember those organized magnetic field lines we talked about in the polarized image? Well, sometimes in this incredibly chaotic environment, those magnetic fields violently collide, snap, and then reconnect. When they do, they release massive amounts of energy and accelerated particles. It's very much like giant sparks of static electricity, but on a cosmic scale.
Section 5. The missing galactic wind. All this extreme activity brings us to a 50-year-old missing puzzle piece that astronomers just recently found.
Think about it. If a black hole is feeding, shouldn't we see the leftovers? Yes, we absolutely should. Theorists have long known that a feeding black hole doesn't just pull matter in, it must also blow powerful winds outward. Even a tiny amount of gas falling in creates enough energy to eject material. But for half a century, no one could find SGR A star's wind. Finally, using the ALMA radio telescopes in Chile, researchers peered through the dust and spotted a massive hollow cone. It's about 3 light-years long and 45 degrees wide, and it's been swept entirely clean of cold molecular gas. The only thing capable of hollowing out a cavity that huge? A hot, energetic wind blowing directly from the black hole. It's a massive absence of material that proves our black hole is very much alive and breathing. Based on this hollowed-out cone, researchers estimate this wind has been actively blowing for at least the last 20,000 years. Interestingly, if you compare it to other supermassive black holes that shoot out massive galaxy-spanning jets, SGR A star is actually in a relatively quiet phase. But finding this wind finally proves that our black hole behaves exactly as the models predicted. It was just incredibly difficult to spot through all that galactic dust.
From a mysterious radio beat back in 1974, to mapping stellar orbits, to capturing a cosmic engine bubbling with magnetic flares and ancient winds, we have come so far in understanding our galactic neighbor. As the Event Horizon Telescope expands its array, and as JWST and ALMA peer even deeper through the dust, we are left with a really profound question. What will the universal laws of these extreme environments teach us next about our own place in the cosmos? Thank you so much for exploring the galactic core with me today in this explainer, and keep your eyes on the stars.